Starting in this video series, I'll talk about number theory based on Searle's masterpiece, A Course in Arithmetic. The book is beautifully written, but in mathematics, the term beautiful often implies difficult or technical. And this book can be difficult for beginners due to the gaps in its proofs. And my goal in this video series, as in other videos I've uploaded, is to provide sufficient mathematical details for all proofs. I may use proofs different from Searle's for some theorems, and I will provide supplementary materials for completeness. So let's get started. Let K be a field, and we consider the natural ring homomorphism from the ring of integers to K, denoted iota from Z to K, by sending the integer 1 to the multiplicative identity 1 sub k in K. And this extends naturally by sending the integer n to the n multiple of 1 sub k. By basic algebra, we know because Z is a principal ideal domain, so the kernel of iota is formed by the multiples of a single element, say n, where without loss of generality, we can always assume that n is non-negative. Clearly, this n is not equal to 1. Otherwise, the kernel of iota is simply the whole ring Z, which means iota is a zero map. But by our construction, iota sends 1 to 1k, so this is not a zero map. Therefore, n cannot be equal to 1. Now we claim that n is either equal to 0 or it is a prime number. Suppose n is not equal to 0. Then, if, on the contrary, that n is composite, say n is equal to a times b, with both a and b strictly bigger than 1, then, by the property of ring homomorphism, iota of a times iota of b, which is iota of a times b, which is equal to iota of n, is equal to 0. And this happens in K. But this implies, because K is a field and therefore an integral domain, iota of a is equal to 0 or iota of b is equal to 0. And this means a or b is in the kernel of iota, which is generated by n. But we already assume that both a and b are bigger than 1. And as a consequence, both a and b must be strictly less than n. And therefore, this is a contradiction to the minimality of the generator n. And the reason that we get such a contradiction was because that we assumed that n was a composite. Therefore, we must have that n is a prime. And this verifies the claim. Now, what does this claim tell us? The claim tells us there are only two scenarios when you take the natural ring homomorphism from Z to any field K. The first scenario is when the kernel of this iota is a zero ideal, n equal to 0. And in this case, iota of Z is just isomorphic to Z. And if you look at the field fractions of iota of z, it is the field of rational numbers. And in this case, we say that k is of characteristic 0. And in the second case, n is equal to p with prime, then iota of z is isomorphic to z mod pz. Because z mod pz is already a field. This is a finite field with p elements. Its field of fractions is just itself. And we use a shorthand notation f sub p for this finite field with p elements. And we say in this case, k is of characteristic p. The characteristic of the field k is denoted by, if the characteristic of k is not 0 and a prime number, then p is also the smallest integer n such that n times 1k equal to 0. Smallest positive integer such that n times 1k equal to 0. Now, we study a very important map in the field of characteristic p, called the Frobenius map. If the characteristic of a field k is equal to p, then the map sigma sending x to the p is an isomorphism of k onto one of its subfields. We denote this subfield by k superscript p. Now let's prove this. Let us first check that sigma is a field homomorphism. Clearly, we have the sigma of x times y, where x and y are both from the field k, is x times y to the p, which by the commutativity equal to x to the p times y to the p, and this is equal to sigma of x times sigma of y. So sigma preserves the product. Then what about the sum? Sigma of x plus y, by definition, is equal to x plus y to the power p. And this may be an exercise you have done in your basic abstract algebra class or number theory class. Is equal to x to the p plus y to the p, which is equal to sigma x plus sigma of y. And this part, if you don't remember, is so-called freshman stream, which is proved by looking at the binomial expansion of this guy. And we want to show that all terms will vanish except the first term when r equals to 0 and the last term when r is equal to p. Why is that so? That is because p always divides the binomial coefficient p choose r whenever r is strictly bigger than 0 and strictly less than p. And this fact is something in elementary number theory. Because what is p choose r? P choose r is p factorial divided by r factorial times p minus r factorial. And this is equal to p times p minus 1 factorial divided by r factorial times p minus r factorial. And now because r is strictly bigger than 0 and strictly less than p, you know that the second part is always an integer, because this whole thing is an integer. We know any binomial coefficient is an integer. Every factor in the denominator is co-prime to p because r is strictly bigger than 0 and strictly less than p, and p is a prime. Because this denominator must divide the numerator, because this is an integer, and this whole denominator is co-prime to p. So this denominator must divide p minus 1 factorial. So this part is the integer, and therefore p must divide this. So every term with r strictly bigger than 0 and strictly less than p must vanish in the field of characteristic p. So this guy must be equal to just x to the p plus y to the p. This verifies this equality. So sigma preserves the sum. And these two, together with the trivial facts that sigma of 1 sub k is equal to just 1 sub k, and sigma of 0 is equal to 0, shows that sigma is indeed a field homomorphism. And now, to show that sigma is an isomorphism of k onto its subfield, it suffices to show that the sigma is injective, or monomorphism. And this is also obvious, because if sigma of x is equal to x to p equal to 0, then immediately we have x equal to 0. And this finishes the proof of the lemma. And the map here is often referred to as Frobenius endomorphism.